In this video, we will learn about measurement in a universe with more than one qubit. The most important thing we will consider is what happens to a quantum system when you measure one of the qubits in the register. We want to know what happens to the other qubits. To answer these questions, we need to generalize the Born rule. The statement is as follows. Let's suppose that we want to measure one of the qubits of a multi-qubit state in some orthonormal basis. Now, we will follow the steps to understand how to predict the probability of a measurement outcome and the corresponding post-measurement state. The orthonormal basis can be given directly, but sometimes it is more convenient to talk about measuring a Hermitian operator. For example, when we say that we measure an operator like Z, this is completely equivalent to saying that we will measure in the basis of the eigenvectors of Z. So that the most general measurements that we will consider in this course are defined by a basis. This basis can be given directly or as the eigenstates of an operator. Let us now go through the steps. Without loss of generality, we can always write the state of two qubits in this form, where the qubit that we want to measure is written in the basis that we want to measure. There will be a properly normalized state accompanying the state corresponding to the other qubit. These states, however, they don't have to be mutually orthogonal to each other. Finally, the coefficients of alpha squared add up to 1. Okay, let's recap. We are going to measure the bottom qubit in the figure, or the rightmost qubit in the equation. Then, the state is written such that the qubit that we are going to measure is in the basis of the measurement. So, the answer to what does the measurement do is very simple. Namely, the probability of getting the eigenvalue corresponding to this eigenvector of the measurement operator is just given by the absolute value of the amplitude squared. So, similar to the one qubit measurement, the state of the qubit that we measured gets projected to the corresponding eigenvector. And the other qubit, the one we haven't measured, is left in the state that it was accompanying to. So now let's go through some examples to better understand how these generalized measurements work. In this example, we start with this input state. I hope you recognize that it is a maximal entangled state, but that's not necessary for the example. Let's say we're going to measure the bottom qubit, the right qubit in the equations, and we are going to measure in the computational basis. The first thing we will do is to rewrite the state in the computational basis. So this is what we have here with the right qubit terms expressed in the computational basis. Now we can apply the recipe. We can see that with probability 1/2, we will project the right qubit into the 0 state, while the left qubit becomes or is projected to the plus state. And with probability 1/2, we will follow the other path. We will project the right qubit into the 1 state, while the left qubit becomes the minus state.